Hi, my name is Dennis, and I'm with Imandra. And today I'd like to talk to you about integrating ImandraX automated reasoning engine via CodeLogician, the LLM integration layer, together with Codex. And our objective is to give Codex the power to reason logically about edge cases because it's very important, especially in safety critical industries like financial services and avionics. So to follow along, you should install the ImandraX extension. So you can do that by opening up VS Code and then searching for ImandraX in the extension search bar. You should also install CodeLogician. You can do that at codelogician.dev, and both will require your Imandra Universe key. And to get Codex to start using CodeLogician, you should use the doc command so that Codex can learn how to write IML, how to interact with CodeLogician. Okay, so the fundamental problem that we have is edge cases are very important. And in safety critical industries, uh, unconsidered edge cases, or sometimes known as unknown unknowns, can lead to catastrophic results. So in financial services, this will typically mean financial loss. So Knight Capital Group is one example, which effectively a broker that disintegrated in the span of a few hours because of a edge case that was undetected in the software that was deployed. BATS exchange before the merger, when they were conducting their own IPO, they failed to do that because of an edge case that was not considered, going from IPO auction to continuous trading. And then the unfortunate debacle with the Boeing 737 MAX program, where there was an edge case that was added to the flight controller software that pilots were not aware of. That unfortunately led to multiple hundreds of deaths, fatalities. Uh, so fundamentally, what we want to do is we want to empower LLM coding agents, in this particular example, Codex, to really reason logically and rigorously about these edge cases so we can provide guarantees and certainty. So we're going to do it by using ImandraX's region decomposition feature. So region decomposition, what it does is it takes a model written in IML, stands for Imandra Modeling Language, and it breaks it down into a finite number of symbolic regions of the state space. So each region contains a set of constraints on the inputs and the invariant result. And invariant result just means if you were to run the model on the inputs that satisfy those constraints, this will be the result always. And typically this result is symbolic. And then we have lots of other features for being able to understand and effectively query the state space for particular information. Because typically in industrial applications, these state spaces become significantly large. And sometimes you're dealing with hundreds, if not thousands, of these regions. And you want to isolate specific functionality, you can do that. So there's lots of functionality for doing that. So let's look at a hello world example of region decomposition, and we'll go for more advanced examples. So imagine we have some code on the left that has a bunch of conditionals. What we're going to do is we're going to say, even though X, the input into that code, can be virtually infinite, so minus infinity to plus infinity, what we want to know is, okay, what are the edge cases? And typically a human will look at this and say, okay, well, obviously there are 4 edge cases here, and that's what we're going to get if we run region decomposition on this. We'll get these 4 regions, and you can see these constraints are non-overlapping, and together they give you the full minus infinity to plus infinity for X as input. Okay, so this is the hello world. Let's now start to go through more advanced examples. And one example in particular that I'm going to show is that of the 6 Swiss pricing logic. So 6 Swiss is an exchange in Switzerland. And this code shows how if there's a buy and a sell order that can trade for a particular market on the 6 Swiss exchange, what is the price at which they will trade? And there is some logic that kicks in based on effects of what the prices are, what the reference price is, the order types, so forth. What's the, not only the best order, but what happens afterwards, etc. So there's lots of non-trivial logic that comes here. And you can see this is the kind of the entry point into the function, and it takes an order book and a real valued reference price. So you can generate virtually infinitely many values that satisfy these types. What we want to do is to say, okay, what is the finite number of symbolic edge cases of how this code operates? And if we're to run region decomposition on this, we would get this nice Voronoi diagram on the right. So you can see this is effectively just listing out all of these different regions. And for each one, you're going to see a set of constraints. So this is, again, machine-generated code that describes what the inputs must satisfy in order for this invariant result to be produced as the output. But in a second, we'll also look at how, what Codex uses this, it's able to generate nice English prose and do many other things with this. Okay, so one cool way to look at this is through a certain structure. So these regions are effectively joined and grouped by similar constraints. So we can go into, let's say, go deeper into these things. You can see the logic is getting more and more complex as we're zooming in deeper into these regions. And so now we have these, for example, these two regions that share all except the last constraints right here. And you can see this once this is different, the output is also very different. So this just kind of showcases how you have these behaviors that are almost exactly the same, but they kind of have one constraint that's off, and then all of a sudden the output is very different. So this is just demonstrating how this technology can pick up these subtle changes in the decision surface that will be absolutely critical in, again, industries like financial services. So this is the straight region decomposition of that function. But as I mentioned before, typically you're dealing with really complex systems, and you want to be able to drill down into specific types of behaviors. And we can do that by adding something called side condition. So side condition is a function that has the same signature as the function we're decomposing, but it also tells us what is the subspace that we're looking for. And here we can add this function, which just says we only want to look at order books that have at least a buy and at least a sell order, and both of them are types of market. And so if we add this side condition here, and we do this decompose, we will get region decomposition, which produces a lot less regions. And something that will be common to all of these regions now is, even if we go deep into something, let's say we'll look at this guy, you can see these. So this is from the side condition that we've introduced to this. So this is just an example of how we can really drill down into particular behaviors that we want to focus on. And there are other features like adding basis functions and so forth. But really, a lot of this functionality has been driven by what we've seen are the demands for rigorous formal analysis of software in the industry. And all of these things come into play for different use cases. Okay, so this is a kind of a nice, let's call it one-step example. But let us look at to now some applications that are really, let's call them intense. And what you're looking at right now is something called a FIX spec. So FIX stands for Financial Information Exchange. And this is a protocol that's used to describe trading APIs. One of them, there are several, but this is, let's call it the most popular one. And you can see here, this is describing really non-trivial logic. So let's go down to some examples of messages. Yeah, so these are all messages. Yeah, this is a logout message and what the possible values are for these different fields. And if we're going to more, so for example, new order single message. So this is what you would want to send when you're creating a new order. You can see all of this logic encoded different types, so forth. And what we have done over the years is created a domain-specific language that allows us to very quickly take this information, encode it in a mathematically precise way, and then translate it to IML so we can perform region decomposition. And so I'm going to show you what that looks like right now. So if we look at this, so this is a similar model to the one I was just showing you. And ultimately, this translates to IML. And the reason why we want to perform region decomposition is because by law, when you're connecting to an exchange, another broker, so forth, you're mandated to perform compliance and certification. So certification should demonstrate that your trading system is aware of the functionality of the system that it is connecting to. In this particular case, it is aware of the logic that's encoded in the fixed spec. And historically, as you can see, there's lots of obviously edge cases, and historically people had to go and by hand think about what these edge cases represent and how many of them are there, etc. Again, fundamentally, the issues there's virtually infinitely many messages or sequences of messages one can exchange with any of these fixed specifications. So that was always something that was problematic. What we've done with region decomposition is we've automated this process. Once you, for example, using LLM, translate that PDF into a way that region decomposition can be applied to, in this particular case using that DSL, what we can do is we can start to really think about what are the possible state transitions of that API, which will allow us to think about all of these edge cases. So here we're not analyzing, we're not performing region decomposition once, but we're actually doing it iteratively over many different events. So inbound and outbound messages. And for example, if we're starting here, if we want to figure out, okay, what does it take for us to go from this kind of state to this state via all of these different events, we can zoom in on it and we can look into effectively different conditions that have to be satisfied for us to get there. And so all of this code you can see was also generated by ImandraX. And this is just to show that this stuff really scales to real world industrial applications. Okay, so now why don't we go into just to position this versus formal verification, which I think is quite important. So formal verification is goal oriented. You have a model, some theorem, and you wish to verify it, or you have property and you want to ask this property of the model and say, okay, does this property always hold true? So it is very goal oriented. Region decomposition is completely complementary and it is discovery oriented. So you give it a model, an IML, it'll describe to you what the different behaviors are. So there's no fundamental property that I wish to verify. We're just asking, what does this actually do? What are the edge cases of this? And again, as I mentioned before, you can slice and dice the state space to really get to a certain level of abstraction or a particular subspace that you're interested in. What type of software does this apply to? Really, any modern software today has combinations of complex state, transition rules, interactions, and variants, and so forth. So even things like obviously API and backend flows, even React user interfaces have state machines. Cybersecurity, this is big. Identity authorization, access control. So really, any modern software today has elements that would be great use cases for region decomposition. Okay, so now how do we connect this feature to Codex? How do we empower Codex to reason logically about code that is generating or analyzing? And we're going to do that by code logician. And ultimately, what Codex is going to do is going to translate the code it's seeing in the IML and then invoke region decomposition and get the results back and interpret them. So it's a very natural way to integrate this technology together. So without further ado, why don't we go and this is our Codex session, so I've been already kind of warming it up so it knows how to use Codelogician by studying its documentation. I've already ran a few examples, so why don't we just go and start asking it to generate some complex code and reason about it using region decomposition. Let's do another example. Make up something complex and apply region decomposition to understand how it behaves. Okay, so it's going to come up with a fresh complex policy example and run region decomposition to end to end. So, and it has already generated this for us. Okay, so now it is going to run Codelogician to check the model and decompose the state space. Okay, now it's done. So you can see here, it really, once it generated Python code and IML code, it was actually pretty, it only took a few seconds to understand the edge cases. So now we're going to go through them and okay, so you see it identified 163 regions by running that region decomposition. So why don't we ask it to describe some regions, let's call it describe the more interesting regions in English prose. So there's lots of, let's call it details that it's playing with restores loyalty. So it has basically generated some code and now it is just saying that there's this non-trivial behavior about some inputs into this thing. So let's call it, let's now ask it, are any of these surprising to you? Yeah, you can see now with Ask Codex, you've generated some code and then you've used region decomposition to understand its behavior, especially the edge cases. And now we've asked it, are any of these behaviors surprising to you? And the answer is yes. So this is really the power of providing this feedback loop immediately into Codex, because Codex generates something, but it cannot exhaustively reason about especially the kind of the tail risk, so to say, edge cases. But this feedback gives it much more insight into that code. So you can see here, it basically says the biggest surprise is how strong the preferred customer long tenure carve out is. I expected it to help, but the decomposition shows it creates a fairly large corridor where the claims and so forth. So let's ask it, would you rewrite the code now that you understand regions? You see, yes, I probably would. And so again, this is something if, for example, when you're using Codex and it's generating code for you, just ask it to decompose the edge cases so it's aware of these things. Okay, so why don't we just do another quick example? Let's do another example that's non-financial. Okay, so do hospital triage policy. And after this, we'll get it to do something that's more front end related. And now it's done. So it's now, okay, generated the code, and it is going to invoke region decomposition now. See, okay, so it is now getting, it only took a few seconds to generate the code, is now processing region decomposition. Okay, so we're now back on track after the Codex tool decided to compact the context. Okay, so we have managed to 132. Any of these regions were surprising to you? You can see again that the tool is surprised by the regions that were produced. Yeah, so okay, let's do another quick one that deals with UI, React-like, and state machines. So just to show how versatile this is. And you can see here that it's actually, when it's thinking, that is what is taking the longest to mount. It's not really kind of invoking code logician and region decomp. It's really all about generating code. Let's go. Okay, it is now doing that. You can see here, it is actually deciding to for event UI traces. So this is, it's not one step, it's actually 4-step decomposition. Okay, it is now adjusting some code. Okay, beautiful. Describe some of the interesting regions. So you can see here, it is now using that information to describe kind of more of the interesting edge cases for how this UI code was produced. So, okay, why don't we now go into, so fundamentally what we're saying here is when you use LLM agents, it's not just sufficient that LLMs are good at generating code for the specifications or requirements that the users provide. Quite often, users themselves do not know what software they wish to generate or create. And by invoking region decomposition early during the design stage, what this allows you to do is to really query the user to make sure that they understand the consequences of the specification requirements that they provide. And that overall leads to a much better coding experience rather than the user having to find out that, you know, the code that was ultimately generated and they're trying to run doesn't meet the requirements. So Codex, using this technology and you invoking this early on, will fundamentally change the way that I'm using this tool. And just to go back and to describe how does this compare with other types of software, we've actually done a benchmark study where we analyzed a bunch of basically problems in logic when it comes to software. So really thinking about branches and things like combinatorial explosion and state transitions and invariants, so forth. All of those things you can find on our website. There's also open GitHub repository that has these examples. But the fundamental outcome is LLMs are incredible at certain type of reasoning, but for these edge cases, ImandraX gives you that advantage of being able to rigorously reason about, what are the important, let's say, changes in the decision surface, so forth. So, uh, so this completes our demo. If you wish to replicate this, please check out our website, imandra.ai. It has all of the links to all of the tools that I have used here today, and happy reasoning.